In this video, I'm going to be running through the questions in your Chapter 13, your overall electricity test, and explaining how the answers to the multiple choice questions are arrived at. And although you have a pretty detailed mark scheme for the last question, there are a couple of things in there that I think would bear a little bit of explanation. The questions in this video are in numerical order, but if you want to go to a particular question, you can skip to it using these timings. In this question then, we have two resistors and they are in parallel, P and Q. We know that the resistance of P is R. We need to find the resistance of Q by comparing it with that. We know that P, which has a resistance of R, is rho L over A. And we know that Q has a resistance given by the same formula, but it's rho over 4 because that's its resistivity, times L divided by A over 2, which is equal to rho L over 2A, which is R over 2. That means that their combined resistance given by 1 over R equals 1 over R plus 1 over R over 2. That's 1 over R plus 2 over R, which is 3 over R. And so the equivalent resistance is equal to R over 3. And that's answer B. This, which looks quite complicated at first, is a simple potential divider question. I've marked point X here, and between point X and point P there's no resistance. And that means that when the contact C is at P, the potential difference between X and P is 0. So that means we can rule out both of these graphs because they don't start with a potential difference of 0. Then really what we have to decide is at point Q, when the contact is moved across the whole 10 ohm resistor, is the potential difference across that resistor going to be 4 or 2 volts? The 6 volt is divided between a 10 ohm resistor and a 5 ohm resistor. Twice the resistance, twice the voltage, so 2/3 of the voltage must be across the 10 ohm resistor, in other words 4 volts. That means that the answer is C and not D. To keep this simple, we'll just do it as a set of proportions. We know that the current is being divided up into 7 different portions, and if we put 1, 2 and 4 here, we can see that the current is going to be biggest in the smallest resistance, and that's going to be 4 times as big as this one and twice as big as that. And so we're dividing it into 7. And we know that it all adds up to 10 amps, so the current passing through the 2 ohm resistor is equal to the 10 amps divided by 7 times the 2 shares that it gets, and that's equal to 20 over 7, and 20 over 7 is 2.86. Which is B. We want to see what happens when we compare the power with the current in a wire which is maintained at a constant temperature, and so we know that it has a resistance which doesn't change. Then we can just use the simple equation which is on the dead sheet, P equals I squared R. Now if R is a constant, that means that any graph where P is directly proportional to I squared will be the answer. And this is C, and we get this parabolic shape for a squared relationship. This internal resistance question then relies on the difference between the 2 volts, which is the EMF of the cell, and the 1.6 volts, which is the terminal PD. And remember that the terminal PD is equal to the EMF minus the current times the internal resistance. Now we know that the EMF is 2, and we know that the internal resistance is 1. And so this gives us a current which is equal to 0.4 divided by 1, or 0.4 amps. In order to find the resistance of the external resistor, then we can just use Ohm's law now. V equals I times R, and 1.6 is equal to 0.4 times R, gives us a value for R of 4 ohms, which is answer D. So the way to keep track of what's happening in a question like this is to make a couple of drawings. So we have 3 identical cells, each of internal resistance R, connected in series. So as a drawing, we have to represent the cells as a source of pure EMF in series with an internal resistance. And we're told that these 3 are now in series with an extra resistor R, and we're told that the current that we get is I flowing through this set of things, and we can call these 3 equal to V. We're told they're identical, so even if we don't know what it is, we know that they're all the same. And that means that the current I equals V over R, in this case is 3V, and the resistors all add together because they're in series over 4R. For the second part, it says if one of the cells is reversed in the circuit, what is the new current in the external resistor? If we draw it again and we do the same thing, but instead of having all the cells in the same direction, we reverse one of the cells, then what happens now is you have V here, minus V here, and V there. The resistors work exactly the same way in both directions, so nothing changes there. So now you have I is equal to 2V minus V over 4R. And that's equal to V over 4R. And this, of course, is 3 times as big as that. And so the current is going to drop by a factor of 3, and the answer is A. Now these 3 cells each have an EMF of 1.5 and an internal resistance of 0.6, and what we're trying to find out is how can we combine them to get a total EMF of 1.5 and a maximum current of 7.5 amps. First thing we can do is rule out this one straight away. The EMF of 3 cells of 1.5 in series is going to be too big. It's going to be 4.5 volts. We can also rule out this one for the same reason, this 1.5 volts, and current either goes this way or goes that way, so it's 1.5 plus 1.5. That has a potential difference of 3 volts, so it can't be that one. Now both of these, this because the current only goes through a single cell, and this because the cells are reversed, means that they both have an EMF potential difference of 1.5 volts. So this could be true. But if we're going to get a maximum current of 7.5 amps, then what we need is for the internal resistance, the combined internal resistance, to only be 0.2 ohms. Now the combined internal resistance of this is 3 times 0.6 is 1.8, and that means the current is going to be less than 1.5. Whereas here, 3 times 0.6, but because they're in parallel, that's divided by 3 to give you that 0.2 ohms you need. So this will give you a big current, and this will give you a small current, and the answer is D. You could do the calculation, and if you do the calculation, you find that you get the right answer. Quite a tricky question, this one. You need to really understand about Ohm's law and where it applies. This is a series circuit, and so that means that the current is the same for the fixed resistor and the variable resistor and the motor. And so if we connect the voltmeter across a component whose resistance is not changing, then that proportionality, the Ohm's law proportionality, will apply. If we put the voltmeter across the supply, assuming that this is not a cell and therefore no internal resistance, the potential difference won't change whatever you do to the variable resistor. The current through the motor will change, but this potential difference won't change. So it's not D. If you put the voltmeter across the variable resistor, then when you change the current through the motor, when you change the current through the resistor, its resistance also changes. And so that proportionality doesn't work either. So it's not C. It can't be A because the same kind of thing applies, but with a kind of extra fixed resistor added to it. In order to have a proportional relationship between current and voltage, you need the resistance to stay constant, and so that only happens in circuit B. So the answer to this one is B, but that's quite a well-known formula. It doesn't take a moment though to show why it's the right formula. So if we have 1 over R equals 1 over R2 plus 1 over R1, and then I've got it this way around because we can then rewrite it as R1 over R2 times R1 plus R2 divided by R2 times R1, which is equal to R1 plus R2 divided by R2 R1 or R1 R2, and that's therefore R is equal to the inverse of that. It's R2 R1 divided by R1 plus R2, which is B. So we apply the potential divider formula to this using the two different values, the maximum and minimum value of variable resistor X. Potential divider formula then says that the output voltage when X is at 5 ohms is 12 times 5 divided by 5 plus 40. And that comes to 1.3 volts. So the answer is going to be either A or B. If we do the same thing for when it's 500 ohms, then we have 12 again times 500 divided by 540, and that's equal to 11.1 volts. And so 1.3 and 11.1, the answer is A. So this initially complicated looking question is actually rather simple. If we know that the current is flowing from P to R, highlighted there, then we can say that this is the low potential and this is the high potential. And we can say that R is at 0 volts compared to P. And if we go from R by this route through Q to P, the potential difference is 6 plus 3 is 9 volts. So we know that P is at plus 9 volts. And that means that the PD between P and R is 9 volts. But the PD between P and S is only 5 volts. So this PD here must be the rest of the 9 volts, and so that has to be 4. That means our answers are going to be either A or C. Now we need to look at the difference between points Q and S. And we know that if this is 0, then point Q is at 6 volts and point S is at 4 volts. And so the difference between them is 2 volts. And that means that the answer must be A, 2 volts and 4 volts. As in turn, a resistance question tests your understanding of how measurements can be used to find quantities which aren't directly measurable. And we have that the potential difference across the cell, which is the thing we can measure, we know that that is equal to the EMF of the cell, which we can only measure without a current flowing, and that's related to the internal resistance by this equation. Now this, when we're measuring V and I, fits the form of the equation y equals mx plus c. So y in this case will be the potential difference, x will be the current, m will be the internal resistance of the cell, and c will be the cell's EMF. And that gives us a form of y equals minus m times x plus c, which is why we get this negative gradient. But the gradient of this graph is the internal resistance of the cell. So the answer is A. The EMF of the cell is the intercept. So the equation that will tell you the resistivity of a material, ρ equals Ra over L, also tells you that the resistance of a given length is ρ over A. But we're told in this question that YQ has twice the cross-sectional area and twice the resistivity of P. And if we double both of these things, that has no effect on the resistance for a given length. So we know that the resistance per unit length of YQ is the same as the resistance per unit length of wire P, and that the resistance is proportional to the length. So we're going to get this straight line, this proportional line that we have in B, and there is no discontinuity when you cross the boundary between the two wires, because the resistance is still proportional to length with the same constant. Ρ over A is the same as 2ρ over 2A. I think it's a bit easy to get confused between the two wires here. So I'm going to draw a small diagram. We know that R1 is longer and thinner, and so I'm going to call the diameter of R1 D and the length of R1 L, and R2 shorter and fatter has a diameter of 2D and a length of L over 2. Now the equation that tells us what the resistance is, R equals ρ L over A, is also R equals ρ L over pi D divided by 2 all squared. Now if we take out the constants from this, we get that the resistance of 1 is 4 ρ over pi times L over D squared, and the resistance of 2 is the same 4 ρ over pi times L over 2 divided by 2D all squared, and that's equal to L over 8D squared times the constant, and that's equal to R1 divided by 8. So R1 over R2 is equal to R1 divided by R1 over 8, and that's just equal to 8. So the answer is A. And what we have to do here is sort out where the series and parallel sections are so that we can work out the combined resistance. So if we start with point X, we have a single 2 ohm resistor in between X and Y, and so that is the beginning. If we go down from X through this 2 ohm resistor, and then at this point here we have 2 branches to produce a parallel section. These come back together again before going to Y. So we can first of all say that these two combined form a single, or are equivalent to a single resistor with a 1 ohm resistance. Now we have point X here and point Y here, and between them we have a 2 ohm resistor in parallel with a 3 ohm resistor. And by making it simpler like that, we end up with total resistance is 3 plus 2 over 6, or 5 over 6. And that means that 1 over R is 5 over 6. So R equals 6 over 5 ohms, which is 1 1/5 B. This question tells us that we're dealing with diodes that have ideal characteristics. And by that, it means that they have 0 resistance when they're forward biased, when they're connected in the forward biased, and they have infinite resistance when they're connected in the reverse bias. And that means that if we start with the plus and go around, we know that this bottom half of the circuit is going to have no effect. It's not going to pass a current. It's going to be as if it were only the top half. And that means that the potential difference across all of this, forget about the 0.6, is going to be 12 volts. And so we have a simple calculation. We have I is equal to V over R, 12 over 2 resistors in series, 60, and 12 over 60 plus 0 through here is equal to 2 over 10, or 0.2 amps. And 0.2 amps is answer C. We can show quite easily that if you keep adding resistors of the same value, 1 over R, the equivalent resistance is 1 over R plus 1 over R, and so on. If you do that n times, then you get n over R, and n over R because it's 1 over R, 2 over R, 3 over R, 4 over R. And the equivalent resistance is the reciprocal of that. It's a constant, because they're all the same, divided by n. Well, this is not a linear equation, this is a reciprocal equation. As n increases, R decreases. So R decreases gives us possibly A, possibly B, but not C or D. But this is a non-linear, this is a reciprocal, so the answer is B. Now this is rather a clever power question, and the key to it really is that it's the square of the current on average, not the average current squared, that matters. So our equation, if it were a constant current, is P equals I squared R, and that would give a power, a constant power. If the current is changing, then it becomes P equals the average of I squared times R, because R doesn't change, so it's the average of I squared. Well, I squared for the first millisecond is going to be 4. I squared for the second millisecond is going to be minus 1 squared, which is just plus 1. And that's going to be the power over 2 seconds, 2 milliseconds. And that means that we could do it for the whole period, but once it's been through that one cycle, the average power is established. And so that's 5 over 2 is 2.5 square amps. So the average power is equal to 2.5 times 100, which is equal to 250 watts, which is C. Okay, so to help work through this, I've done a sketch and included the formula here. What we want to know is which of the following things, which of these 4 things will make the PD across the thermistor increase. That's this potential difference V out here that I've labelled here. So if we increase the temperature of the thermistor, its resistance will drop. So R2 will go down, and then the ratio R2 over O1 plus R2 will also go down. And that will mean that this potential drops instead of increasing. If we increase the variable resistor, that makes this number go up without changing that one, and so that has the same effect of reducing the potential difference across the thermistor, the V out. If we reduce the EMF of the battery, then we reduce this value here, and everything here stays the same. So again, it will drop. So what we need to do then is this adding a resistor in parallel. And what that will do is effectively make R1 smaller. The effective resistance between these 2 points will be less than R1. And if R1 is smaller, then this denominator decreases, and so the whole fraction increases, and so V in times that increased fraction gives you a larger value. There are a couple of ways to do this question, but I think this is the most straightforward. What we're going to do first is work out the current in the circuit. The I equals V for the total circuit divided by R for the total circuit, which is 6 divided by 15 ohms, and that's 2/5, which is 0.4 amps. Now we know that power, that's the power with which energy is dissipated in the internal resistance of the cell, is equal to I squared times the internal resistance. But we also know that energy is power times time, and so energy is also I squared times the internal resistance times the time. So now we have a single formula to work out the answer. The energy is 0.4 squared times 0.3 times 60 seconds, not 160. And that gives us an answer of 28.8 joules, which is B. The mark scheme is pretty comprehensive here, but there are some points to note. First of all, if something's in bracket, it doesn't need to be in your answer in order for you to get the mark. So for instance, for the first one, if you say that Ohm's law is obeyed initially, then you will get the mark even if you don't say this leads to the graph being a straight line at this point. However, underlined things have to be in the answer in order for you to get the credit. So if your answer says that the filament heats up, but it doesn't say it heats up because the current is big, then you don't get that second mark. And in this last question, we have this resistor being set to 0. Now these two currents come into this junction and out of here, and that means that I1 plus I2 must add up to I3. But if the potential difference across here is 10, and this has no resistance, then the potential difference across this must also be 10 because those two are in parallel. Effectively that resistor isn't there. The current in I2 will be determined by the potential difference across R2. And we know that this has a potential difference of 12 volts, and this is a potential divider. We don't even need to do the potential divider equation because we know that this has a potential difference of 10 volts, and those two have to add up to 12. So this has a potential difference of 2 volts. So I2 equals V over R2, which is the 2 volts that are left over when you take the 10 away from the 12, divided by the 10 ohms, equals 0.2 amps. And finally, we're asked to explain what will happen to the potential difference across this resistor if this resistor is changed from 0 up towards the 10. And again, we need to just either apply the circuit rules or the potential divider rules, which is just a formation of that. If this resistance increases, then the potential difference across this will get a share of the 10. This will drop from being 10 because this will get a share. The potential divider will become balanced more in the favour of this R1. And that means that this drops from 10, but these two still have to add up to 12. And so if this resistor has a decrease in potential difference, then this resistor has an increase in potential difference. And one of the things you pick up from the mark scheme is that you must say actually what happens, state and explain.